Okay, so let's try this video recording thing. Alright, so today we're going to talk about step growth polymerization. So this is just an example of some commercial step growth polymers. We're going to talk a little bit about specific examples of these later, and we're going to have a lot of videos today too, just to try to give you more of an idea about things about polymers. So step growth polymers can be classified by the functional group present in the polymer backbone. So we'll talk about esters today, carbonates, polyurethane. Specifically, we'll talk about Kevlar. Nylon is a big one. So we've compared step growth and chain polymerization a little bit before. But step growth polymerization can be classified into two basic groups. One, you have the reaction between two different bifunctional or polyfunctional monomers. So having like a diacid and a diamine to form a polyamide as an example. You can also have the reaction between one functional, bifunctional, or polyfunctional monomer, which has both types of functional groups. So this would be like an ARB example, so then you're going to have an ARB polymer. So an amino acid would be an example of this, having like an ARB, and that will give you something like a polyamide. So in many step growth reactions, there is a low molecular weight byproduct that is reduced. Because this reaction is in equilibrium, the byproduct has to be removed in order to push the reaction to the right, and then therefore give you high molecular weight products. So this is often called a condensation polymerization because something like water or methanol would be removed. So the terms step polymerization and polycondensation are, for historic reasons, often used synonymously, although it's not always correct because an example would be polyurethane where you don't actually have anything removed. So you couldn't call this a condensation reaction. So for the general mechanism, you just have a monomer, and a monomer gives you a dimer and a monomer gives you a trimer, etc. You have the rapid disappearance of monomer species. The reactivity of the functional groups is somewhat independent of your chain length. Your molecular weight will increase slowly. You don't need any initiator, although a catalyst can always help your kinetics. And at the end of a polymerization, your chain ends are still active, therefore you can form things like black copolymers. For step growth, you have a high degree of polymerization only at high conversions. So you need a highly efficient reaction, no side reactions, and therefore you have a limited choice of functional groups A and B. So the reactivity of your functional groups is usually largely independent of your chain length. So the ways to tailor molecular characteristics, there's a lot of them. So for your prereqs, kind of as mentioned before, you need a high reactivity, high selectivity, and no side reactions. So there are different kinds of functional groups you can have in these type polymerizations, anything from something very flexible, something very rigid, polar, non-polar, etc. So then there's a chemistry that has to be between the reactive groups. So if you looked, before we talked about an A, an R, and a B, so this would be something that would be considered the R. You can have something, again, rigid, flexible, hydrophobic, hydrophilic. These are all going to give you some different properties, and we'll talk a little bit about that. So some basic chemistry of carboxylic acid derivatives. There are many different ways you can form polyesters. This is your basic polyester right here. This is just showing you that there are different reactants you can use, or different looking reactants that can all lead you to a polyester. And again, all of these have different byproducts, that condensation product that's coming off. Polyamide, same thing. There's different reactants that can lead to a polyamide. A polyimide is a common carboxylic acid derivative, polycarbonate, and polyurethane, which we're going to talk about later. The accessibility of functional groups. In order to get a high molecular weight polymer, the polymer cannot precipitate from the polymerization mixture before the desired molecular weight is reached. This can often actually be kind of difficult. You can see with nylon we're actually going to get the polymer to precipitate. So anyways, this is due to a limited choice of solvents that dissolve the polymer and also dissolve the other things in the reaction mixtures. So something that dissolves the monomer and the polymer, for example, can be hard to find. So you can see here, using different solvents can affect the molecular weight with ethylene glycol. So here your polymer is precipitating at once. This way it doesn't precipitate until after a half hour. And this one, the polymer is completely soluble, so this will help increase the molecular weight by changing the solvent. You can also have, so I sort of took out some of the kinetics here of these slides just to be able to put some other things in, but what those slides would have shown is, like with other polymers, you have the assumption of equilibrium and equal reactivity of functional groups, but that's not always true. So depending on what your functional groups are, you can obviously have different reactivities that exert a mutual electronic influence. So an example of that would be a polyurethane, where one isocyanate group activates the other by electron withdrawal. Once that first group has reacted, the reactivity of the second group will then decrease, since the urethane is much weaker. So just know that that kind of thing can exist, where you're not always going to have the same functional group on either end. Actually, go ahead and skip that slide. So equilibrium considerations. Most step polymerizations involve equilibrium reactions. Thus, it is very important to elucidate how the equilibrium affects the extent of conversion. So to do that, you compare a closed system to an open driven system. So in a closed system, none of the products of the forward reaction are removed. So in this case, you'd want to remove that water in order to push the reaction this way. So if you're not doing that, that would be a closed system, where you can get the reverse reaction of depolymerization, going back this way. So in an open or driven system, one of the products, usually the condensation product, is removed from the reaction, and therefore preventing that reverse reaction. So this is the ideal way to do this polymerization. Alright, so for a closed system, or equal, I thought I took this slide out. I think I did. Don't worry about this. Okay, so for an open-driven system, as can be seen, high molecular weight polymers require an open-driven system, as I sort of mentioned already, and at least one of the products of the forward reaction has to be moved. It's easy to do this with certain volatile low molecular weight byproducts like water, methanol, etc. And this can be considered condensation. Hydrochloric acid can be removed in the same way, or by having a base in the system to actually just neutralize that acid. And sometimes the byproduct can be eliminated because it precipitates. And we'll see one example of that. It can be a problem to drive the reaction towards very high molecular weight, since all the small molecules need to diffuse out of the reaction. So purification can therefore become a little bit tricky with these, depending on how of a high molecular weight you get. You can also get cyclization in these types of polymers. So we've talked about what that means before, having these rings present. You can get that intermolecular, where the same exact chain reacts with itself, or then you can have intramolecular, where two polymer chains will form together. Okay, so The production of linear step polymers is sometimes complicated by the occurrence of cyclization. Ring form is often observed in both an AB and an AABB type system. So in AABB, only molecules with unequal end groups usually react to form rings. Obviously, ring formation is quite undesired. Alright, so this is showing you an example of the cyclization of an AABB. So if we have these two reacting with each other, this is the AA, this is the BB. You can see here we've reacted them together. At this point we've just reacted one more monomer. So here we actually have two A's next to each other that are going to form a ring. And so instead of this polymerizing, it's actually just going to react together here and form a ring. So there are thermodynamic considerations of a cyclization, and the thermodynamic stability really depends on the ring size. So similar to what we've talked about before, with how easy it is to polymerize a ring, this sort of has to do with the stability, right? So these are the least stable rings, all the way up to 6 being the most. So if you're forming 6-membered rings, you're probably going to be stuck with 6-membered rings. If you're forming something down here, these are probably going to break back apart and drive you towards the linear polymer that you want. Kinetic feasibility of this happening also really depends on the length of your polymer chain. So you can see here we have a shorter polymer and here we have a longer polymer. So as the potential ring sizes increases, meaning here, the molecule can adopt a multitude of different conformations, few of which involve the two end groups being adjacent. So it's a lot less likely for this to form a ring because the odds of these two ends seeing each other becomes a lot less. Whereas this one can easily find different conformations in order to react with one another. You can also, so depending on what your chains are, if you have some of those stiffer middle groups like I talked about, that can also decrease the feasibility because your polymer is not going to be moving around as much. Depending on how good of a solvent you have, that can also decrease the chances of this happening if you have things that are really, really soluble. So for molecular weight control in these types of polymers, since your degree of polymerization is a function of time, it can, in principle, be controlled. So the reaction can be quenched. Let's say if you know that at time 30 minutes your molecular weight will be X and you want it to be that, you can throw something in to stop the polymerization and give you that molecular weight. So a problem here can be that sometimes your functional groups or end groups will remain intact. So if you then heat the polymer up again, you might get continued polymerization. Depending on what your groups are, if there's something like an amine, excess heat or something like that can actually lead to degradation, and that's actually just going to break apart the polymer. So you can sort of simplify this by adjusting your stoichiometry. Oh boy. Not what that's happening right now. Okay. So by adjusting your stoichiometry, so you can use one of your monomers in excess. So if we use this in excess, you're going to get this to form, and then this is something you can easily just remove from the reaction after it's over. But knowing exactly what this mole-to-mole ratio is between this and this will actually allow you to give you that molecular weight control. Okay, so some polymers, like polyesters and polyamides, can, under appropriate conditions, undergo interchange reactions. So that's transesterification or transamidation. And so you're basically just getting you're getting functional groups within the polymers to react with one another. So they can react to yield one longer chain and one shorter chain. And so the molecular weight distribution is actually probably not going to change here, but it can. Alright, so getting into certain examples of very common step step growth polymers, polyethylene terephthalate, or PET, sometimes it's called PET, P-E-T-E. It's one of the most important commercial polyesters on the market. You may not have heard of Dacron or Terylene. Mylar is a very common commercial name of PET. So you can get high crystallinity. It's pretty cheap, actually, price-wise. It doesn't soak up too much water. It has very good mechanical properties, meaning that it has very good strength. And it also has really good chemical resistance. And it's soluble in very, very few solvents, which is good for chemical resistance. So PET, you can make it into fibers. So that's if your molecular weight is above 15,000. These kind of fibers are used for a lot of different clothing, curtains, upholstery, fishing line, things like that. You can also make them into films, usually by melt extrusion. So these are used in audio and video tapes, floppy disks, which I'm pretty sure don't even exist anymore, capacitors, 35 millimeter films that boil in a bag stuff, like if you were to make rice or vegetables and you boil it in a bag, that's usually PET. Again, Mylar is a trade name by DuPont, and then ICI and Hoist is actually where these trade names come from. For bottles, so your molecular weight has to be greater than 25,000, and this is it becomes solid after the condensation. And so this is what a lot of like plastic bottles are made out of. So low crystallinity preform, and you basically stretch, blow mold those water bottles into what they are. Alright, so for the synthesis, in the first stage, you're going to have a mixture of this dimethyl terephthalate, excess ethylene glycol. You just heat them under a normal pressure and gas with a catalyst, and then you get methanol that is released here, and that's going to get removed. Alternatively, you can have a reaction of terephthalic acid, but don't worry about that. The second stage, the reaction is kept molten, meaning it's kept in the melt, and the temperature is increased. Before it was at 150, now it's at about 270 to 280. Another catalyst is added, and the pressure is reduced to effectively remove that ethylene glycol, because remember we used an excess up here. So polycondensation catalysis by soluble antimony through metal coordination. So this is similar to stuff we talked about last week, but you can use these types of catalysts to really make this happen a lot faster, which is, industrially how that's going to go. Okay, so I've actually just uploaded these videos separately, but I thought some of them are a little boring, I'm going to admit, or they play funny music, but I think they are pretty good at showing you some things. So polyethylene terephthalate, this is a good video that shows sort of how this is made, and it has awesome music too. Okay, so that kind of felt like a love story to me, but and also a Coke commercial randomly at the end, but that sort of shows you visually how that PET is formed. Okay, so this one is a little bit long, but I think it's kind of cool in itself because it really shows you industrially how some of these polymer plants and things like that work. So this is one of the biggest PET process plants in the world. It's actually in New Jersey, so you can see it makes 500 million pounds of fiber grade PET per year and 500 million pounds of bottle grade PET. I think the difference there is really molecular weight. Sorry, my computer likes to do that. So the video will start at some point, but this is just kind of an overview of all the different kinds of PET that this facility actually makes.
The International Process Plant's PET facility here consists of a manufacturing site of approximately 100 acres fully fenced and 1 million square feet under roof. Major raw materials, terephthalic acid and ethylene glycol, arrive by railcar and are unloaded in the raw material area. They are then transferred to the raw feed mixing system in the monomer plant. Isophthalic acid, IPA, the third major raw material, arrives by truck. The polymer control room is the center for central process control, controlling the polymer from raw material mixing through cut resin. The control center also has the capability of controlling the 7 fiber polymer lines. The computer-based control system controls the key process parameters for both monomer and polymer production. The PET process raw materials are mixed in a feed system and then transferred into a 2-vessel monomer plant with a capacity of 70,000 pounds per hour. Monomer is then transferred to the polymer processes H9, H10 or 11 and H12. H9 and 10 are Tashi designs and have a capacity of 14,000 pounds per hour. H11 is an ICI Celanese design, has a capacity of 24,000 pounds per hour, and H12 Zimmer design has a capacity of 31,000 pounds per hour. H9 and H10 were upgraded to PET lines in 1993. H11 and Phase 3 monomer plants were completed in 1994, and H12 was completed in 1997. All polymer lines are equipped with high-speed chip cutters with interchangeable spares. The spares allow for continuous polymer production during required changeovers. Cut resin is then transferred pneumatically to the solid-state polymerization facility, the SSP. All of the SSP units are Buehler design. There are 3 units. P1 and P2 have a capacity of 14,000 pounds per hour, and P3 has a capacity of 31,000 pounds per hour. P1 and P2 were completed in 1993, and P3 was completed in 1997. The amorphous chip goes through several stages, including crystallization, solid stating, and cooling, before being transferred for loading into trucks or rail cars. The utilities complex of the plant provides all site energy streams, including hot oil heating, steam, chilled and cooled water, compressed air, and inert gas. All utilities process equipment is controlled through the utilities control room. The site has a 750,000 gallon per day capacity activated sludge water treatment plant. Process water is supplied by 4 deep wells on site. Fiber production has 2 monomer plants, 7 polymer spinning machines, supplying 18 draw lines equipped with crimping, cutting and baling with a capacity of 500 million pounds per year. Finished bales are transferred to a fully automatic warehouse with a storage capacity of 21 million pounds, and additional flat warehouse storage of 4 million pounds. In summary, the site consists of 100 acres of fully fenced manufacturing space with 1 million square feet under roof. Manufacturing capacity of 500 million pounds per year of fibre and 500 million pounds of PET resin.
Alright, so that just kind of gives you an idea of something, of a polymer plant. That is obviously a little bit old, but they still all look like that today, except maybe with more modernized computer systems. But so Lubrizol actually kind of looks like, a big part of it looks like that, as we make a lot of our own polymers and a lot of our own different reactants that go into all of our oils. So a lot of chemical engineers and polymer engineers are who really works on that stuff. The chemists will sort of do the chemistry side and then also work on helping the scale up of the reactions into those big reactors that you see, and then the engineers sort of control all the reactions in there that happen afterwards. So, I know all of you are, some of you are chemistry undergrads, but going into polymer engineering is not something that is out of grasp without an engineering undergrad degree. A lot of people I went to grad school with do stuff like that now because they were more on the engineering side as opposed to the chemistry side. Okay, so the other thing that we've mentioned a lot before is extrusion, and I sort of explained that and pulled up a picture a couple weeks ago about extrusion, but I don't think I ever really did it justice. So I'm going to sort of show you two videos that give you a better idea about how a lot of these polymers are actually processed. This one has great music.
Freeland-Wade plastic tubing is used in countless applications every day. In fact, the company likes to point out that today you probably either use their tubing or something made with their tubing. The base material for tubing is called resin. It starts off as tiny pellets. This is polyurethane. The process starts with a vacuum hose lifting the resin pellets into a hopper. The hopper has an integrated drying system to make sure that no moisture gets into the extruder. Colorant is also in pellet form, and it gets added to the color hopper. The heart of the extrusion process are these long augers. Their complex shape is tapered, specifically to maximize the mixing, heating, and moving that the resin needs to get through the extruder. The extruder has several heaters along its line. To get the pellets to melt completely and move through the extruder, each stage in the extruder is set to different temperatures. With the resin ready and the extruder preheated, it's time to start the extrusion process. At the start of the run, it takes a few minutes to get the temperatures to stabilize and for the color to get into spec. During this time, the extruded plastic is allowed to fall to the floor to create what the employees call blobs. These blobs will be recycled. Once the color is right, the operator cuts off the blob and feeds the tubing into the cooling trough. The trough is filled with filtered and chilled water. The cool water serves to set the hot plastic into its final shape. The tubing is held under the water by a series of rollers. At the far end of the trough, a laser measures the outside diameter of the tubing. This data is fed into a computer that continuously monitors to make sure that the tubing remains within spec. The tubing is pushed by the extruder on one end and pulled by a conveyor at the other. keeping the tension exactly right is critical to maintaining quality. Until the tubing meets their standards, a bin is used to collect the tubing. This tubing will be recycled. Once the computer tells the operator that the tubing is in spec, the operator measures manually to confirm. Then it's time to start filling the reels. Throughout the process, the operator is measuring frequently to assure quality. Extrusion is oftentimes just the starting point for the tubing. There's also a secondary production process for tubing variations. Worry-free Freeland-Wade tubing is always an exact fit, with an on-time delivery rate.
Okay, so that kind of gives you a better idea of what extrusion looks like. What that didn't really give you was an idea of what goes on inside the extruder before it gets to that water part, where they did show you those two rotating screws, but not exactly what it looks like inside. So this is kind of showing you how this works. This is a quick one.
As the raw material moves along the screws, it is mixed and conveyed by the various screw elements. If we look at a cross-section of a twin screw element in the barrel, we can see how the flight of an element affects the raw material. Within each screw element, there are 5 mass transfer regions where transfer of the melt takes place. These regions are the channel, the overflight, the lobal pools, the apexes, and the intermesh. We'll look at each of these regions separately. The channel here is the same area as the one we earlier called the screw channel. This is an area of low shear in which the amount of raw material fed into the extruder affects the rate of mixing. Of the 5 screw regions, the channel is the one with the least amount of shear effect. Running the screws with more plastic raw material causes the screw channel region to be more filled. If there is more fill in the channel, there will be less shearing and mixing of the plastic. The overflight is flow between the top of a flight or mixing element and the barrel wall. This is a very high shear area. Lobal pools are the pools of raw material captured by the pushing flight flank or lobe. For example, a wide kneading element will capture a large dispersive lobal pool, while a narrow kneading element divides the melt into streams, capturing a small pool of melt.
Okay, so that just kind of gives you a little bit of an idea of how the material looks inside those screws. Depending on the speed of the screw and the pressure and the temperature, that can produce a lot of different characteristics within your polymer. And obviously, just based on those 5 regions that they show you, it's a lot more complicated than that. And so there are, entire classes we take on flow characteristics and extrusion and rheology and things like that. So it can get really complicated actually inside that screw, and the parameters you choose to make everything through that extruder is pretty intense. Okay, so some other technologically relevant polyesters. There's polybutylene terephthalate. So it's got pretty similar characteristics to PET, but it crystallizes a lot faster, so that can be better for certain engineering applications because you have a faster mold time. You can have a copolymer, a PETG 1,4-cyclohexadiene terephthalate with PET copolymer as well. You can have different aliphatic polyesters. So these are used as non-migrating plasticizers for PAC. So for elastomeric polyurethanes, you can have different bioabsorbable or biocompatible polyesters, like polylactic acid is maybe something you've heard of. That has a resorption at a rate comparable to wound healing. So they're trying to make a lot of gels and different things with lactic acid that they can put cells into and sort of help with wound healing. There's also some liquid crystal polyesters. They have a really, really high improvement in mechanical strength compared to PET, so that can be used in certain applications where strength is needed. Sure, you've all heard of BPA and the "oh my god, there's BPA in my water bottle" fiasco. So that's bisphenol A polycarbonate. It's a polymer. So you see the structure right here. It's pretty much amorphous. It doesn't really have a whole lot of crystallinity. So that gives you superb optical quality, which is why things like water bottles can be clear. It's got really good mechanical properties. It's very tough over a wide temperature range. It's also why it's good to drink things out of. You can see this is a lot more expensive than that $0.6 per pound with the PET. It doesn't really absorb water, has good chemical resistance. It does have FDA approval, and there's obviously that big question, is BPA safe or not? So it's used in baby bottles, a lot of medical applications, glazing in some of windows, safety helmet visors, protective eyeglasses, and CDs. General Electric makes Lexan, and Bayer makes Macrolin, and then I'm not exactly sure who makes Merlon, but that is another trade name for polycarbonate. Okay. Alright, so this I thought was kind of a cool video. It gets a little redundant after a while, but this is just sort of illustrating the immense strength of polycarbonate. Demonstrated. This is from a motorcycle website. I apologize, the quality on this video is terrible, but you can get the idea. All that happens now is he just starts to get out bigger and bigger guns, but I think you get the point. I think at the end it's a clip of acrylic versus polycarbonate, which one would you choose? So I guess if you're riding down the street in a motorcycle and there's shooting going on, you'd be safe, but anyway, it's obviously something a lot stronger than an acrylic polymer. Alright, so something I know you've all heard of is nylon, and nylon is a polyamide, and it's a very famous polymer. So in 1934, Carruthers at DuPont invented polyamide 6,6, which is the first synthetic fiber, and that is actually what these type of nylons are made out of. So there's kind of a lot of history behind nylon, and so I just kind of threw some of it in there, but in 1930, the first guys at DuPont that tried to polymerize caprolactam to nylon 6 said that it couldn't be done. In 1934, the same person and a different person at DuPont successfully polymerized the first ethyl ester, which formed a polyamide 9. And so the thing about polyamides is every number is quite different. So having a 6 or having a 9 or an 8 or something like that really changes the properties. So about 2 months later, another guy in Carruthers' lab made a polyamide with even better characteristics. It ranged from 5 to 10. So this is a 5 to 8 example here. So basically the numbers here are just the two different monomers that are reacted. So this is a 5 group and this is an 8 group. So 6, 6 would be 6 here and 6 there. So in 1934 then, triggered by the business people at DuPont, they were concerned that 5, 10 to 10 was too expensive to make. So Carruthers started to screen a series of polyamides, which from 2 to 10, which gave you a total of 81 different candidates. However, only 1 year later, in 1935, this guy in the same lab gave the first example of polyamide 6,6. The polymer had pretty exciting properties, and the economics of the polymer were right, so that is the candidate that DuPont selected, and therefore polyamide was introduced to the market. Okay, so polyamide 6,6 or nylon 6,6, it's known as all these different things, has moderate to high crystallinity. It is 130 a pound, so it's more than something like PET, but not quite as high as some of the others. Has very good mechanical properties, which does change with its water content, limited thermal stability, good chemical resistance, and it was soluble in few solvents. And nylon 6 is predominantly synthesized by ring opening polymerization. Okay, so for amides you can have fibers made by melt spinning, or so they contain high strength, flexibility, toughness. So a lot of carpeting, many clothes are made of nylon, tie cord, fishing nets, seat belts, and obviously hosiery. Engineering plastics is another application. They're often reinforced with glass fiber or mineral fillers. So these are used in automotive, fenders, your lamp housing, roof racks, engine fans. Electrically it's used. It's also used in ski boots, kitchen utensils, different toys, etc. And aromatic polyamides will give you things like Kevlar, which we're going to talk about. So polyamide fibers, they are very good at hydrogen bonding, so they can create ordered polymer chains that are very crystalline. You can have hydrogen bonding and other secondary interactions that are holding your chains tightly together, and this will make them difficult to move and slip past one another. So this means that a nylon fiber doesn't really stretch all that much. Alright, so the below is an aromatic polyamide. That's that Kevlar, and Kevlar, the primary use of Kevlar is a bulletproof vest. Okay, so polyamide 6,6 synthesis. So synthesis by interfacial polycondensation. This is called the nylon rope trick. So you're going to have a rapidly stirred mixture at room temp over organic solvent, adipoyl chloride, water-soluble base, and hexamethylene diamine. So you're going to actually get the polymer that forms right at the interface. It's kind of a cool thing to see. I'll show you in a second. The polymer product precipitates and is continuously withdrawn as a film, so you sort of have to pull the polymer out of the solution as it goes. The reaction is a little mechanistically different from step growth, as the monomers diffuse at the interface will only react with the chain ends, and the reaction rates are extremely high. Okay, so this is an example of nylon synthesis.
Polymerization is the process where smaller molecules, called monomers, link together to form long molecules, long chains called polymers. Polymerization is the process of those monomers forming long chains. Now, the chains of molecules can be extraordinarily long. In fact, you can make essentially indefinitely long chains of molecules. And Lonnie's preparing that here. He's mixing sebaceous chloride in carbon tetrachloride with hexamethyldiamine in water. Those two solutions don't mix, but at the interface between them, the molecules combine to form a polymer. And Lonnie can actually reach in and grab the forming molecules and pull them out in a long chain. The molecules will continue to polymerize. So as he draws the molecules out of solution, the final product, the monomers continue to react at the interface and form more polymer. In this way, he can make a long strand of nylon, a synthetic polymer. Here you can see the nylon forming at the interface between the liquid layers. Nylon is an important commercial material because it can be used to form fabrics. And it revolutionized the fabric industry because nylon is cheap and easy to make and can replace cotton and natural fibers in clothing and other products.
Alright, so that is called the nylon rope trick. And so the other thing I wanted to show you is Kevlar. So that's what those bulletproof vests are made out of. And that's just got a really rigid aromaticness to it, which is why it's so strong. Alright, so as you can tell, Kevlar vests are made with 16 layers, and so I don't know much about guns, but it looks like one of the guns made it through 5, so you can see that's pretty safe. As I'm telling you this, I'm realizing in my head that I'm saying something wrong. Where are we at here? Is this drawn wrong? So nylon 6/6, for example, well, that's showing you 510. So what it's supposed to mean, the 6/6 is not actually about what you start with. It's about what you end up with. You end up with a repeat of 6 different carbons in the center. So this 510 right here, this is 5 and this is 8. This should be a 5-8. So whatever you end up with as your repeats should be what it comes out to be. So I apologize. Anyway, don't have to worry about that. Okay, so polyurethanes. So this is the structure of a polyurethane. Commercially, they're produced mainly either as fibers or foams, although there is also biomedical applications of polyurethanes. So you get a selection of different diisocyanates and diols used in commercial polyurethanes. So actually the Brecksville site, the home care site at Lubrizol, makes a ton of polyurethanes. That's one thing we make a lot of it from biomed applications and other things like that. So a lot of our extruders and things like that are actually used for polyurethane. So we have an entire diisocyanate tanks and diol tanks and things like that on site. And we do make, so polyurethane fibers are commonly, so you've all heard of spandex. So we make a lot of polyurethane fibers that go into a lot of underarm products, like Victoria's Secret bra straps. Then there's some other like stretchier type material on Nike, Adidas, clothing like that that Lubrizol makes. So commercially, it's the most important polyurethane fibers are those that result in a blocky copolymer, which is the spandex. To make these low molecular weight, polymeric diol is reacted with excess isocyanate to result in an isocyanate terminated polymer. So you have excess isocyanate here. This is your alcohol, and then so it's gonna create this. You're gonna have some unreacted left, and that's gonna react with this diamine group. So you're gonna end up with a soft segment and then also with a hard segment as well. So we've talked about this before, what happens when you have soft and hard segments in a polymer chain. So you're going to get aggregation of these hard segments. Sort of pseudo crosslinks or physical crosslinks. And this formation is thermally reversible above the melting temperature of the hard segment. So polyurethane foams is also an important commercially class of polymers. They're often based on TDI and polydiols. You have to add a small amount of water to create these, and that increases the molecular weight by the formation of a urea linkage, and you also get the release of CO2. So a lot of, like insulation, things like that is made of polyurethane foams. Alright, I think this is the last video we have today. This guy's kind of funny.
I've looked through hundreds of chemistry textbooks and seen thousands of reactions. One reaction I see more often than any other one is A plus B yields C. It's in all the kinetic sections in the textbooks. It's in a lot of other sections, and it is the only reaction that always works and does exactly what it's supposed to do. And I was just overjoyed when I discovered that, in fact, there are reactions that say A and B, and you can put them together. I always thought they just made those things up. And so here I've got something that says polyurethane foam, and it says A and B. And the instructions in this thing say mix equal volumes of A and B together, and you'll get C. Or in this case, I guess you get foam. Your students probably have seen or purchased at a hardware store or someplace like that some of those things they call goop and foam and insulation products. And they may have asked you, what is that stuff? How does it work? Now you know the answer. It's got A in it, and it has B in it. And you can explain it to them immediately. You put A and B together inside the can, and then it shoots out the front. Well, it's nice to look at that. So we're going to take a look at A and B and see how they behave together. So I'm going to take some, I bet we have to do it alphabetically, so I'll put some A in first. And I've measured out carefully a volume. That looks like enough. Now the really hard part is getting the B in, because this requires calculus, because this is a cone-shaped object, and to get the volume exactly the same, I have to be very careful. Now, fortunately, these cool goggles that I got from Flynn are calibrated on the inside, and as I look at this, I can tell exactly when I get equal volumes. There it is. I know I'm not supposed to hold it up quite so high, am I, guys? So I'll hold it on here, and I've got exactly equal volumes. I need to stir this up. in a relatively short period of time, we'll see something interesting happen. A plus B will yield C, and it's actually starting to do that. So I'm going to set this off to the side over here and just let it go, because I want to do another one while that's starting to take off. I like this. I liked it in a cup. It's kind of neat. It goes up. I always thought it would be neater to do it in something more interesting. And I had these laying around the lab trying to think of something to do with it. It also eliminated the necessity for calibrated goggles, because when I measure this one out, I can do it digitally. I can add 2 fingers of, wait a second, my fingers are in there, so maybe I'll put another glove on. Oh, hold it, I've got a different kind of glove to wear here. Ha. I will put in, if I can get my hand in here, I will put in 2 fingers of A. That's accurate to 2 significant digits. So there goes 1 finger, 2 fingers. I get really confused sometimes when it goes in the thumb. I have no idea how much I've got in there. And I'll put in 2 fingers of B. Oh, look it over here. That's going to be really cool inside the glove. And 2 fingers of B, or thereabouts. We can tie this off. Maybe. Without too much trouble. I like this too because it's got a great mixing system. I wasn't brought up on a farm, but I really get the feeling that I could be there now. Let me use this for training for young farm students. And we'll mix that stuff together. And now this, by the way, is a little safety piece of information with this. And shortly this is going to start to expand, much like this is doing. And the glove will get bigger and bigger. Occasionally, it will burst. And if the polyurethane foam system hasn't set yet, it'll shoot the stuff out. This is not something you're going to pass around in your class. Don't give it to one of your students and have them hold it in their lap. You can see it's starting to grow now. The principal comes in. It's a great thing to have him hold on to, or her. Let them go there. This does get to be just kind of like this. All right, that's about set. So I'm going to put that on top of there. Will it stay? Yes! That's the polyurethane foam system in the glove.
Alright, so that was just a funny way of showing how polyurethane can foam. Alright, okay, I finally figured out what I was doing wrong here. Thought I was losing my mind. Hold on. Figured out why I was confused. Okay, this is nylon polyamide 510. So you have a reaction of 5 and 8 here repeat units. The reason I was confused is because I wasn't even thinking about the fact that these were carbons. So you have a 5 and then 8, 9, 10. So this is a polyamide 5 because there's 5 carbons and then 10 carbons. So sorry about that. I forgot that these were carbons too. So this is a 510. So then here, when you have nylon 6,6, this is 6, and again this is 4, 5, 6. So that produces nylon 6,6. Okay. Alright, so we have polysiloxanes or silicones. I know you've all heard of silicone. So polydimethylsiloxane is a commonly used silicone. It's very stable at high temperatures, water repellent, chemically stable. So this is commonly used in hydraulic fluids, so this is what I do. We do use quite a bit of of silicones. They're actually really great anti-foam agents, and that's what we use them a lot for. Greases, lubricants, heating baths, anti-foam agents, elastomer applications, so sealants, caulks, adhesives, tubing, medical applications like heart valves. They can also be used in paint, electrical insulation, things like that. They're very amorphous.